看你等下有没有录，不知道，我记得他一定要啊，对啊，我记得好像要这样才能录音。
The main thing is to compute these guys. So all the computation now is going to use it to know how to compute the following. Okay? So just to remind you, so this is given. So what we need is this rho, which would be like the equilibrium density matrix. Corresponding to the total Hamiltonian is H0 plus H perturbation. But equilibrium here is a not good term. It's not a good term because this Hamiltonian can depend on the time. So if the time is changing, also the rho would change with time. So this is the density matrix which corresponds to such Hamiltonian, but we cannot call it equilibrium density matrix if there is really some explicit time difference. So this is just that telling us a nuance. Okay? So the goal is we need to compute this thing. So if I don't have this guy, which is in principle time dependent, then I'm not able to move the function. Okay? Okay? Clear, right? So the main point is how to compute the guy. And the naive guess would be like that. That's all we will say, okay. So for the original Hamiltonian, rho 0 looks like that. So first try can be that someone says, oh, let's try that. A to the minus beta H0 plus H pep as a function of time. But of course, this will not be the case. This is not true answer. So it's not so simple. Okay, so this doesn't work. So we really need to do something more. And the main point is that, okay, we will try to look for the solution of this operator rho t as a operator rho 0, which we know, plus some also small perturbation f as a function of t, which is the operator of that. Okay? And what we need to do, we need to write the equation for this and solve the equation for that. So when I was doing the reminder about the quantum mechanics, just a reminder continue, that we know that if we have a pure state psi, then we are having the Schrödinger equation to compute the time dependence of the state. If we would have a density metric rho, then the Schrödinger equation for the density matrix looks differently, and it's almost identical, and this is very important thing, that there is a small difference compared to the Heisenberg picture, that this is the equation which describes the time derivative of the density matrix. So the order is changing. Yeah? I was just giving you before equation of motion in the Heisenberg picture, but this was the Heisenberg picture for the operator. But rho is a state, so it doesn't follow the same equation. Yeah, so just keep in mind that. Or are you familiar with this, what I'm writing here? Do you see that this is the correct way how to do it? It's very easy to see that because we can write that the density matrix at time t would be nothing else as the state c at time t and c at time t, right? And we know that this is going as e to the minus h bar h0 times c0 c0 and to the plus h0 t. If I would have a summation of such things with some probabilities, then it will directly go like that. And if you make a time derivative, you will get it. Okay? So you can just quickly check it by yourself that it comes from that. Okay? So what we need to do is that we would like to now solve this equation for that guy. So we are taking this equation. This is nothing else. This is the same as the Schrödinger equation. This is not the Heisenberg equation that I want to represent. Okay, so we take that and we are going to write this equation. So if I am making of the light, so once more, I will write it like that. So we are going to solve this equation now. This is the total Hamiltonian. Okay, and maybe I start to say a little bit so much. So if you are doing it, then making the time derivative of that is very easy because this is the constant density metric. So the derivative of that guy is 0. So what I am having on the one hand side is EH time derivative of this unknown thing which I'm calling a T. Right? And on the right hand side I need to write the Hamiltonian. So this is the commutator and this is my original Hamiltonian H0 and perturbation. And then this is the operator rho 0. And okay. Everything in the Schrödinger picture. Now I'm using Schrödinger picture. Okay? Great. So we now need to unpack this operator. So if you are computing, then we are getting 4 terms. The first term is this one. Yeah, the second term is this one. The other term is this one. And the last term is this. Okay. Keep in mind what I said before. Rho 0 is just the function of h, so it is a to the minus beta h0. And any function of the Hamiltonian and the Hamiltonian formula is equal. So this term is trivially 0. Right? Because they are computing. Okay. This term we will ignore, and we have a reason for that. We are doing just the linear response. So we are looking for the response to the first order in the H. Okay? These would be first order in the H, but also perturbation is the first order in the H. So there is like this is the first order in the H, this is the first order in the H, so the commutator order is the second order in the H. Like it's a higher order, it's the higher order of finding the value. Okay, just solving the problem for the first order in the H. Are you understand what I'm talking? So this term is basically the term which is the higher order in H. Yeah? So this is somehow proportional to the H. This is proportional to the H, but this is proportional to the H squared. And the right hand side is proportional to the H. Yeah, because we assume that perturbation which is proportional to this function H, yeah, will also affect these to the linear perturbation. Okay? So this is the assumption that this term is in the higher order, so we are ignoring it. So if you would like to do the generalization of the Coulomb modulus going to the second order, you cannot do it. Okay, but we are going to the first order. What remains here is basically just the following form that we are left with the equation which goes like this. And I will write it a little bit to the different one. Not different one, I will put the thing on the other side. So I will write it like that. The E, H, some very clever observation. So one can clearly observe, so this is I'm writing it as a clever observation. And this clever observation is that you can check, or we can quickly check it, but I'm leaving it as a homework. It's trivial. The main observation which I'm trying to say is that this thing here is this thing. Should I show it or you quickly see it? It's basically just the differentiation of the exponential function like here. Yeah, so because if you are now making the derivative of that, including the e, then you are basically getting first term that you differentiate that, you will get e divided by h, right? Then you are getting h0 here. Then you repeat everything. These three terms, one term, second term, right? Then I'm getting e h bar. This term, this exponential is untouched. Now I'm differentiating this guy. This guy is untouched, and then I'm getting the last term. The last term will be minus because there is a minus eh, right? And then I'm getting again all those three terms because this is the third exponential, right? Great. And here I'm having h0. Great. Okay. And I will just look for the following things that now these exponentials which are outside are chosen like that they are cancelling all those exponentials which remain here. So should I do it or can I just comment it? Can you tell me? It's up to you. Do it. And then we will not maybe finish everything in one day. Okay, so then let's make it. Then let's calculate it. Okay, then I'm going to calculate this thing somewhere. Okay, but I will be lazy, so I will use the operator u, okay? So then what we are having here, that I'm writing that u, I have it here. Then I have e h bar, then I'm having the derivative of time, okay? And then I'm having this operator. U, f, together, okay? Multiplied by 2. And here I have, sorry, together. Okay, so I introduce these I introduced before, right? So this is together, this is very okay. So let's make it. Okay, this EH bar I will take outside. Okay. Now I will have the following things. This is 2. And now I'm having 3 terms. Together with differentiated F2 to together F differentiated with together F okay. Multiplied by together. Okay. This is nothing else as sorry, differentiated as e 1, and then I am having again 2 is meeting 2 level, which is 1. Then I have F, then I have this X0, right? And then 2 is meeting 2 level, which is 1. So, H is given, right? And this is the minus commutator. Was it clear? Okay. So, fantastic. So we now agree. So we continue with this. So then let me erase the thing. Here. So taking this fantastic observation, we immediately have the solution. So we would have immediate solution, taking into account this clever observation. I see that if I don't write it in my notes, directly with the clever observation, that I can directly write. So the solution of that, if you are using this clever observation, if I'm writing this clever observation as I did before, so once let me write it like that, this is a U, okay, and this is the E, HE with respect to ET, and here I am having U dagger at U dagger, then I can immediately write the solution of this problem, and the solution of this problem is that. So I can write it like that, that EH bar total derivative of there U dagger of U is now, and I am now multiplying this equation. Okay, write it like this. This is equal to the condition H cap as a function of P times rho 0. I just rewrite it, right? Okay. And now what I can do is that I can act on this equation from the left by U dagger and from the right by U. By doing that, I'm killing those two guys. Right, but I'm producing them here. So let me just writing it. So if I'm just writing it, so I'm getting that this is the same as the U dagger as U. And here we are having U dagger commutator H that U. And now that is integrated. So if you wish, this is now very easy. I'm just making a comment. So I do everything filled out in the Schrödinger picture, but if you wish, this is nothing else as this F written in the Heisenberg picture. And this is nothing else as this commutator written in the Heisenberg picture. I'm not using it, but I'm just telling you that you can find the solution in the textbook that people write it, the solution in the Heisenberg picture. Because this is just directly in the Heisenberg picture. But now you can integrate it directly in this equation. Okay, so you can just directly integrate it. Alright, so we will get something like that. That would be, okay. So it would go U dagger at U. There would be 1 over 2H. There will be some integral. And then inside of this integral we would have this expression. So let me write it. So it will be integral over tau. And now I'm writing it. So I'm returning back the two names. So it will be a to the plus e divided by h bar h0t or tau. Then I'm having this Hamiltonian pair as a function of tau. make the commutator with rho 0, then I need to put this A, U, the minus H, 0, tau, right? So I need to make this integral plus the value at the minus infinity. But in the minus infinity, the Hamiltonian is 0 because we were assuming that we are adiabatically switching on. So I don't need to write the solution, because then I need to write also the Rudiger f minus infinity. But in the minus, because I'm integrating differential equation, right? So if I'm integrating differential equation, that something with respect to time is equal to something else, then the solution is that this is the integral of f plus x at initial time, right? Because we were assuming that we are turning on the perturbation from minus infinity. I was turning on adiabatically. That's exactly the point, which I was not saying, or which I was wanting to emphasize now. Okay, so all the bits I was saying, we put the perturbation slowly enough, or such that the system is not perturbed dramatically or something like that. It means we need to do it adiabatically. That in the minus infinity, we assume that there is not a perturbation. And now this function h as a function of is slowly turning on. And now we are measuring and computing. Okay? So that's why we are going from time in the minus infinity. Okay? Okay, in general solution there will be also such term, but this term is 0 because in the minus infinity the system is still not unperturbed. So in the minus infinity the system is original system is the equilibrium. Okay? So there is nothing like that. I just want to tell you. Okay. And now still we need to bring these operators on that side. Okay? So I again need to multiply these things and bring them on that side. So I am now writing the final formula. Okay? Which would be good if you don't keep it on the blackboard, so I will write it to the corner. So now we are having the solution of that, and we really know this Ft, and you see that it looks horrible, and you'll say, oh God, what we can do with that. But you will see that it looks horrible, but it's effectively not so difficult to handle it. So the final solution, if you are looking at that, I'm just making it, I will put it here and I will try to keep this corner attached. That F operator at time t is now, and I need to put U. So okay, now basically I'm doing again the things that I'm multiplying this equation by U from the left side and by U dagger from the right side. And by that I am killing those guys effectively, but I need to correct them. Right? So the final thing is on that, and it is 1 over dh, right? And then multiplying by U means that I'm getting A to the minus E divided by H A0 times T. Now we are getting this crazy thing, this very crazy bracket. So this is the integral from minus infinity to the T. Integration variable is denoted as a tau. Okay? And now I have this A to the plus A divided by H A0 tau. Now I have the commutator. Perturbation tau rho 0 minus E H 0 tau. Right? Then this integral finished here. Right? And now I'm multiplying with the plus E divided by H. Okay. Yes? X0. Okay. Did you get what I was doing? Was it clear? Okay, you see it's too many letters, but effectively, in Heisenberg picture, this equation was very simple. In Schrödinger picture, it looks a little bit more complicated, but the main point is that thing, I also write the same thing in the Heisenberg picture. So this is in the Schrödinger picture. So this is the first time I'm putting S number, okay? To emphasize that this is the Schrödinger picture. I can write the same thing in the Heisenberg picture. The formula is much simpler only optically. Because in the Heisenberg picture, this is just the integral from minus infinity to times t tau. And now what you need to do is that you need to take this operator h step. You need to go to the Heisenberg picture, make it as a function of tau, and compute it with rho 0. Okay, so you definitely agree that it's much shorter, apart that there appear this in Heisenberg, which you really need to compute means you need to really do these sentences which are, they are not just written there. It's like introducing new symbol to make it shorter, but effectively for computation it's not optimal. Okay? So this is the things, and now we know that density matrix for the Petrov system at time t, that it is the original density matrix and this f. Okay, I put here. Great. So this was the first big thing which we needed to calculate it. And now we need to compute the expectation value. Okay? So what we now need to do is that now we are having this, and now we need to start to compute the expectation value, and that's what we do. So guys, are you understanding what I'm doing? Everyone is understanding? If you will not, then you are cheating on yourself. Actually, calculation is pretty trivial. Only too many letters and just one is to keep that in mind. But even if this is not clear, then please tell me. Are you clear? Can I understand it clear? Perfect. So now we are able to compute what we wanted, and this is the change in the variable a and derive the Kubo formula. So now we are in the position to compute this thing, which was trace rho t of the operator r minus trace rho 0 of the operator r. Okay? And we clearly see that this rho is nothing else as the rho 0 root at the, so at the end, this is nothing else as a trace or of ft, all in the Schrödinger picture. Okay? Great. So we are having the thing here, right? And we bring it here. So we are able to compute the trace directly. And for trace, I will use the following things. So let me just write it here what I will use. Let me just summarize that. So and I will use the following things for the trace. And when we will use it, then I'm using the properties. So what I will use, let me just write it. You're going to have to know it, but just to have them. So I'm using the properties that if you are under the trace, you can always make this cyclic perturbation. Yeah, if you have any operators under the trace, this is the same as the trace of CAD. Or like that. So you can make any transformation. So you can always move it like that. Cyclic perturbation. Okay? The second thing which I'm using is that if I have a trace, and then I have some integral over d-dimensional space R of some operator O and blah blah blah. This is the same as the integral over d-dimensional space R, and this is the trace of operator O and blah blah blah. The trace is a linear operator, and the integral is nothing else than linear. So it's also linear operator. So yeah, I can change it. Is that last thing which I will use, and this comes also from Daddy's, and I will just write it, that if you have the trace, and you are having, and this is the things that this is the bracket, it's not the commutator, now I will have a commutator. I don't know, sometimes, this is, sometimes we need to pay attention for that, so this is really the commutators. So this is the same as, let me change the bracket here, let me use some bracket. Doesn't mean anti-commutator now. No, I think we are running out of the bracket. So I can just use this bracket. So this is the same as a trace of this is the commutator. Which is the same as a trace. And I can change the order. I will use this speaking now going further. Good. So what we need to do now, is that I have this 1 over h, right? Then I have the trace, this is this trace. Okay. And now I have this bracket, and I have this integral from okay, and what I can still do, guys, I'll just maybe just tell you that since I'm integrating over tau, I can put also this guy inside if I want. Because it's harmless, okay? And also from that side I can put this inside the bracket because this is the integration over the thing. Okay, so I can put it inside. And even because those things are commuting, I can even write it in the better form that I can write it in the A0 tau minus t. So what I can do at the end, okay, now I will write it. Okay, so this is the trace. Minus infinity to t integral to tau, and what I have there, what we now do, so it is tau minus t then I have this h factor tau 0. Okay, then I can also put this thing here, it will be minus h. This is the h0. Okay, and now I need to put this operator R. And now I can start to use these properties that, okay, if I want, I can put this operator here because I'm under the trace. I can use this property that I can take this thing, which is in that K00, so I can take it out, things like that. This thing I now brought in the Heisenberg picture for some reason. Because I was, I think, already annoyed to do it like that. So, okay, that was like I already did the Heisenberg picture. And this is time t. And this is the operator R. The Heisenberg picture at time tau. End of the commutator, end of the base. Okay, so here you need to plug the, from this exponential, you again need to dissociate these two exponentials to the original terms, and the terms with the time, t will come here, and the terms with the tau will come here. It is just again, like always, redoing the rewriting of the code. Is it fine? Can I leave it like that? Your studio are not at the end. Only I'm just writing how it is, how it looks like. But you see, do you see that it's trivial? Danny? No? Well, what is the problem? Just tell me. I don't want to fix it like that. Oh, Heisenberg picture is very simple. By the way, 100 years from quantum mechanics, so you should remember it. What I was doing here, if you can just plug it here, plug the same for the perturbation in different times, and this will produce this two exponential. Okay? This was the main point. Okay. And still, don't remember the last point which we're going to do is that h pairs was written as some integral of the operator O. So let's still need to write it. So as I was saying, we are still not at the end. But we are almost at the end. And this is the most tedious but trivial calculation. Believe me, it's very trivial. Okay. But you will see that it's very powerful, and we will still massage it to some much more user-friendly form. Okay. So now we are using the thing that the perturbation was this integral of a three-dimensional space, this function, and the operator OR. So I'm now plugging it there. And I will just write it, it's a 1 over E H. And this will be the integral from minus infinity to time t, integrated over tau, integral from over the whole volume. So I'm not writing from minus infinity, but it's a multi-dimensional integral in principle. But it's over the volume of your system. And then I'm having this trace which I had before. And this is the original density matrix of the unperturbed system. So all the information about the original Hamiltonian H0 is given in this density matrix. And now I am having the commutator of the operator A. At times t. Okay, it can differ from the position or something like that, but it's at time t. This is the thing which t and t is the same e. Okay. And then we are having this perturbed Hamiltonian in the Heisenberg picture at time tau. But only these things we are having. Operator O at times R times tau. End of the commutator. End of the bracket, where there is the function H. This is the final settlement. Okay. So T is here. Okay. This is the point that we are looking. So this is basically here. So the argument of Z. So it can be in principle position dependent. nothing else. The integration variable is r, and r is entering only here and here. Okay? Integration variable tau is here, and tau is entering here and here. Okay? And it is exactly the form which I told you before, that we can write this in principle as the following integral. It introduces this generalized susceptibility, which will be the function of r0 at r and t0 at t tau. That will be compared to the classical function of theta. And you see, so this object here basically is complicated. Are you fine? You see? Guys who already gave up, letting them go, or I don't know. It's killing me, it's one of the toughest calculations today. This is the most general formula. It's called the Kubo formula. So this is the formula which relates generalized susceptibility. And some people even write the all here because you need to know which operators you have in the game. Right? So this is the operator A, so normally it's the first one, so it's written generate. So you need to put the indices of that. And this is again the function that you are looking for the response of that at some time. And also we can have a time t0 that we are looking for. Or this is the time t. This time t0 is 0. I can call this t0. If I want to have a response at some time t0, then it will be this time. This is not the integration variable. Okay, so this is the Kubo formula. And you see that the Kubo formula is, if you just look at this expression, this is the trace of the rho zero. So this is the equilibrium expectation value of some crazy operator. So this generalized susceptibility, if you look for the form, check in, you look tired. I was thinking you would be excited. You're terribly excited. Okay, so the formula for the generalized susceptibility. And okay, so here is the integral. I just want to make a comment. So here is the integral from t0. Some people like to write the integral over time from minus infinity to plus infinity. So the way we need to do is that if we want to write it like that, then we need to do one trick here, and we need to put here a theta function. And then this is a guaranteeing that the integral is only going to be 0. Okay, this is just a trick to write it. So now I can write the Kubo formula in its full beauty. After lengthy derivation, derive the Kubo formula for generalized susceptibility. I was short to write it. So phase over rho 0 is nothing like that. So just remind you the different directing these. That is means that it's the phase with respect to rho 0. And sometimes people take this e and put it into the denominator and then write it as a minus. You can find it in the book like that. Okay? So this is the final outcome of the linear resistance theory. And most important formula for that. Great. Okay. Do you have any questions? Yes. From A? Yeah. So this is the thing which connects the experiment.
Yeah, I
theory.
mean, if I want to calculate the theorem, so I will A. So,
Yes.
So it depends if my A is something from R or a single variable.
So the A is your operator. So your operator can be local or global. This I just want to say that you can do the following measurement. Okay, just let's discuss it just so you understand what you are doing. So let's say this is my system. Okay. This is my Hamiltonian A0. I can take the local operator out. So what I can do? Mathematics, local operator. I'm writing the local operator. Operator which has some index R0. So what does it mean experimentally? For example, that you are doing some STM measurement. You put your tip here at point R0. You put some backgate voltage, okay, here, and you try to make some tunneling experiment, okay? And you record your data. You measure some quantity, okay? Now, you apply the external perturbation. So you take your system and you make the external perturbation, for example, because you put your system through the magnetic field. So you apply the magnetic field, and I will make the same experiment. Putting your tip at point R0, measuring the data. Now you take these two measured data without magnetic field and with magnetic field, and you make the difference. So you take the data of your experiment at point R0 with the magnetic field minus data at point R0 with zero magnetic field. And then you go to Unau, his theorist, and he should be able to calculate it. And what he will do is he will calculate this thing. Right? So, but what Unau you need to know. So your measurement is some STM. So you need to know what is the operator corresponding to STM. And you would tell him, I need the data in the magnetic field. So he'd say, oh, here should be the operator magnetization. And then, if he knows to diagonalize the Hamiltonian or things like that, he will be able to compute it. And if you are matching, then you will look and you will show your experimental data, and you will show your theoretical data, and you will get a track. And then matching, you are not publishing the paper. Okay? So this is the things how we are doing. You can take another quantity that you measure, which is not local. You measure something global. I don't know, so what you will measure as a global, you will just look for the emission of the light from the whole global thing. So you put your sample in some cavity, and you measure the total energy which was radiated from your sample. And in that case, you have some another operator which does not depend on R0, but something global. Okay? And then you again apply the magnetic field, and again do the same thing. So this R0 just wants to tell you that you can have the measurement or the measurement which is local, so you measure something at some point, or it can be something which is not local, which means like energy, total energy would be able to make something. I don't know how to measure total energy. It's calorimetry. that case, there will not be any R0. It will only things different from time. Okay? Got it? Do you understand what we are doing? Any other questions? Now we are having a break. You can use the break for anything. Guys, how many of you are lost? No one is lost. So how many are in? We have a problem with classical logic because there are also guys who didn't do the superposition. We are purely quantum. Okay, so now let's make it okay? If you have a question, you can use it for this. Okay, but I think I will leave that as a homework because I think I will not be able to do it. I think then I will, I think I prepared too much for the few hours. No, CDOs is writing on the blackboard, so maybe, but you prefer that I'm doing on the blackboard, but I should make a slide and just show over the calculation of the slide, and give you the slide. Blackboard is better for you. Yes, different types. Oh no, so the upper limit I just put the theta function.
Oh.
So like basically we just wanted to integrate from minus infinity to sine time t0 some function which exists here. So I was just making it to infinity and just put the function is 0 here. And how to put it 0, you just put the theta function. For higher arguments, so t0 minus. So if t is larger than t0, then theta function is negative, and theta is negative 0. So we basically extended function triviality to 0. Was it? Okay, sorry. This was not clear then. But please ask me.
So this is the student function over
Yes. No, in principle, it's not necessary. Because we can have a operation R can be, you know, like operation R can have some vector indices. It can be the electric field along x, y axis, and this H field can also be a vector indices. So it can also have some Cartesian indices.
somehow fast.
So I want to just make a remark, okay? So remark number one, and very important remark is that actually this function, if you really carefully look about, is just the function which depends on the time difference. So it's the function which depends on R0, R, but there is just a difference of T0 and minus. So it does not depend on two times. It just depends on the time difference. And it's, again, can be, it's trivial effect, again, just playing with the things under the trace. So this is the commutator. So all the times what I can do here is I can put this exponential, just moving it here because they are next to each other. And this one, I can make the road around the globe. I can put it here because it's cyclical symmetric, right? Under the trace I can change the order, I was telling you. But because this is e to the minus beta 80 and this is also 80, so I can commute them. So it can jump here, and then it can jump here. This is the reason what you will do is that you can put all the time dependence only here, and what you will get here at the end is just the minus EH, and there would be 80 T0 minus tau, and here you will have at the end e to the plus EH 80 T0. So you can put those things just on the one place. You don't need to keep the time itself. Okay? Very important property. So 80 is only depending on the time difference. So this is purely general. This is the purely general fact. Which again just comes with playing with the commutators and things under the tree by the rules which are in the okay? Good. Second remark. If you have a spatially homogeneous system, like 2D infinite electron gas, 3D super large homogeneous sample, then this function is also just depending on the difference of the position. But only for the spatially homogeneous systems, this function is only depending on the difference between the different vectors. So it does not depend on two vectors position, but just on the difference. And this is because if you have a homogeneous system, there is all the such functions have the property that if you have a general, if you have a system which is homogeneous, then if I add here plus some lattice vector L, then the value should be the same. If it's homogeneous, it shouldn't change a little bit. So then basically this means that it's the function which is different from the difference. Okay? But this is only for the homogeneous system. And since we will deal with the solid, homogeneous solid, we will assume that. Of course, if you do the atoms, you can also make the theory for the atomic structures and molecules, then this is not the case. And in that case, it really just depends on two positions. Okay? Good. Second, other important remark is, okay, as I told you, this H0 can be arbitrary Hamiltonian, which is time independent. This is important thing which I want to emphasize. Remark 3, H0 is any Hamiltonian, single particle, many body particle. Important thing is time independent. Which means we are having some equilibrium situation. We are able to talk about some equilibrium because this is this Hamiltonian which give us this averaging A0, or which are giving us the thermal equilibrium density particle zero. Okay? This is the other important thing. Okay? Fourth important thing which I want to emphasize, there was already a question from the audience, but that time I didn't specify that. Okay, other things, okay, so on there. This function is called retarded. Sometimes it's called retarded generalized susceptibility or retarded response function. The word retarded means for this theta function. Yeah, retarded is related with this theta function, T minus T0, and it has a very important thing that it tells us that measurement should follow after the perturbation. Okay, so this is the time of doing perturbation. We are doing the perturbation in times tau. Even continuously we can do it. But we are doing the measurement at time t0. Right? And we should do the measurement after the perturbation. System cannot know response to the perturbation which will be applied in the future. Now we are having Trump, so we absolutely don't know anything. But this is a really important thing. Yeah? So perturbation, so measurement follows after the perturbation. Okay? And this is included in that. So it's a retarded, so it means like that we are getting the information about the system later after the perturbation. Okay? Did you get it? How you look that you will be able to? It's fine? Fine. So that's a retarded means this means that measurement is done after the perturbation. Okay? STM, which I showed the picture, we should after that we apply the magnetic field. Okay, not opposite to that we are measuring and now we start to apply the magnetic field. It's not corresponding to the situation. So also in the laboratory you should first apply the magnetic field and then turn your STM or something like that. Okay, so the order matters. Okay, this is important thing. Okay, this time and step. Okay. The last. Okay, and one thing which was R5, which is important, that I'm always taking this turn, and this was really sudden. It was very, I said it, and it was not very loud, and you were not asking me about that, but now it's really time to say that this perturbation of the Hamiltonian field, we're sending a picture, should be turned on adiabatic. This was like saying that we write this Hamiltonian, like all the music of this Hamiltonian we hidden in this function, so there was integral over the space, right? And then we put some operator R, okay, this is some operator R, and then we put here this function RT. This function RT should be such that if we are going with the time to minus infinity, then this function is going to 0. Okay? So perturbation is turned on, and it's turned on adiabatically, which means like this is the thing. Physically, what this corresponds to the situation is that at time t minus infinity, you have your equilibrium system at given temperature, which means temperature is fixed. So basically, you know what is the equilibrium situation that you are having. That okay, now I have some electronic states. Some of the states are occupied. Okay, because I have a thermal occupation. I don't know, something like that. Others are empty. Those which I call as occupied are full. Some of them are empty. Okay. Now I prepare such system. I put the system into the contact with the thermal bath, this created with this. Now I remove the bath, and now I turn the perturbation, and the perturbation starts to act on this system. And basically what it will do, it will change the separation between, I don't know, electronic level. But it cannot change the occupation. This means this adiabatically. We are assuming that all those states, if they were occupied, are staying occupied. They can change in the energy. Okay, the energy can be changed. Okay, 1, 2, 3, something like that. So this means this adiabatically. And adiabatically means that there is no production of the entropy. Production of the entropy means that you will change the occupation of the different energy levels. This is not allowed what we are doing. Okay? So this linear response is assuming that the perturbation is adiabatic. And there is such things which are not normally set to the link directly, somewhere later or maybe never. But this is important as the assumption. For these reasons, for example, if you would like to do light and you would like to take a sample and shine on that as a perturbation some light, which is harmonic light, monochromatic light, and we would like to know how the system absorbs. These will both be in this category because if you are having light, then normally this function, if you are taking some harmonic function, then this function would look like some f to the e omega r minus or e k r minus omega r. Because this function would look like if I'm having some harmonic perturbation. So now we are in troubles because this can know, but this is not blah blah blah. So the people are also were able to treat this system. So if you have a harmonic perturbation, which we will have many times, what we need to do, we are making a trick and we put the convergence factor. So what we will do here is we add the factor delta, where delta is a small infinitesimal number. If t is going to minus infinity, and this is a positive number, basically what I'm doing is that I have a harmonic signal, and if I'm going to the infinity, basically I am always compressing the number. If I put it in the time, it will look like this. If this is the time axis, let's say this is the minus infinity and here it is the present, then I have a signal which is going like that and we are attenuating it such that it's going to zero by this convergence factor here. So the thing is like that. So if you would like to apply the harmonic perturbation to the system, we always then need to put our form of the function like that, as I wrote it like that. So this function we always explicitly need to write that is, let's say, harmonic function. But the harmonic function, you keep in mind, oh, it's not decreasing to the infinity, so I need to improve it, so you will add this to it. And then you need to keep this guy and put it everywhere with you. Then it should go with you to keep the things, okay? Because if you will not do that, some integrals can stop to exist or things like this. And we will see it like that this term is important, because otherwise we will get some infinity. Or we will get some singular integral. Are you finding that what I said? I think you will see it later, but I'm just trying to tell you that maybe you see already that this trick is done. But it's important to mention that. And the last but not least, you can put part of something, but there is no factor. Okay, the last thing which is important, which I want to say, which is the Riemann number. Okay, I think the Riemann number. The Riemann number 6. Very often we, and also our friends from experiment know that many times we don't look for the response in the real space, real side, but rather in the K space and the frequency domain. Okay, so very often what we will do is that we will not look for the functions r0 minus r and t minus tau, but we will look for its Fourier transformation. So what we will do, we will make the Fourier transformation of this function like that. And because this also has a physical meaning exactly like that. If you probe your system by the harmonic rates, then this is the basically nature of response that you want to have. So we need to then make the Fourier transform of this, and this Fourier transform will be integral dr dt, right? And we take our function rt and the r to the to r. So I need to change each conventional for the Fourier transform to the knowledge of the beginning, but I will do it later. But we will very often do calculation in the Fourier transform. Okay? Great. And then the thing which is beautiful about the Fourier transformation is that if you remember how the Kubo formula looks like, so the response or change of the response at point r0 t0 was expressed as the integral over dr dt, and here we have our function r0 minus r and t minus tau, and there will be special field rt. if you look mathematically at this equation, what is the form of this equation? How it looks like? Did you heard something as a convolution? So you see that this is the convolution of two functions. That the convolution means that you are always pairing these things together, right? Oh, sorry, this is the form. Like this. So it has the form of the convolution. Generally, the form of the convolution is that it's the integral by x, and we are having h minus or integral of x, or something like that. The integral of this form of convolution. And the beautiful thing about that if you make the Fourier transform of that, what come out that the Fourier transform of the convolution is just the product of the Fourier transform. So what happens is that if I know the Fourier transform of this equation, then if I know the Fourier transform of this equation, I will get that response delta A q omega is nothing else than the product of the Fourier transform. Okay? So, in the Fourier space, this generalized full formula looks even simpler. It's just the product of two functions. Okay, but we still need to compute like that. Okay, because of the convolution. So do you know these things that the convolution, Fourier transform of the convolution is the product of that? So this is basically used like that. Okay. So what we see is that if you have a perturbation with the wave vector q on the frequency omega, then also the response is on the same wave vector and the same omega in the linear response. Okay, so you are not producing nonlinear optics. This is not nonlinear optics. In nonlinear optics, you are able to change the thing. If you would like to have a higher things, you need to go to you need to do not the linear response, but you should go beyond the linear response. You need to calculate something more. The term is ignored in the equation. You remember I was making some commutators, and one term I ignored because I said it's higher order in omega, or higher order in the perturbing field. If I will not do that, and I will solve it more solidly, then I will also be able to get correction to the linear response. But in the linear response, if you perturb the system with some frequency, also the output is on the same frequency. If this is not happening, then you can say linear response will not work for the system. You can throw it out. You say, okay, it's bored, we cannot use it. Because if you see this, it's the manifestation of the nonlinearity. Okay? So I can just prepare you that the life can also bring this. An experiment can show that the linear response is not well justified to use. Okay? Good. Or you shake it too much. If you will do it smaller amplitude, maybe it will still remain linear. Okay? Good. So, let's go far away. So guys, till now, clear? Let me know. Some fingers like up, down. Give me some symbols like I don't like it, that I can change also. I need a linear response there, so good? Clear. Now we're gonna to massage this formula far away to the way that we are able to compute something, okay? You know, I have a PhD and basically what I'm doing, I'm just cleaning the blackboard. I didn't know that this would be my life. So guys, if you want to go for PhD, please go. Maybe if you can find a better room with larger blackboard. Okay, so we go to very important thing. Okay, I said that thing with the delta we will do, and we go to the paragraph 2.4, which is called the spectral also called the Lehman a manager node, Kramer's chronic relationship. Okay, so assume now that I am really able to know the eigenfunctions and eigenvalues of this Hamiltonian. I'm able to solve it. N is the collection of all quantum numbers. So assume that I have it. So N is basically like the composite index, so this is the all quantum numbers. That specify the given state. So it can be K vectors, E, sublattice index, and things like that. So this is like the all quantum numbers which were available. So this is our formula for the response function. I will just write it like, okay, 1 over EH again, and then what we have is the theta function. Okay, so it's just different on the time difference. I'm just writing here as a function of time. All these R and R0 I am not writing here, I didn't operate it later. And there was this 1 over Z. And there was a trace. And then we had e to the minus beta h. And I'm now 0, right? This was this thing. And I have this operator A at time tau. Okay, in the Heisenberg picture. Then there is the operator O. And then I have it in the opposite order. Minus O. So I already used this trick that all the time dependence I can just put into one of these operators. Okay. Perfect. So if we are making the trace over these quantum numbers, and since I want to save some writing, then what I can do is this is the same as writing it as a trace, and then it's basically doing the whole compute the expectation value with respect to this system. This is the trace explicitly, right? I was writing you how to compute the trace of the operator, like rho 0 A. You remember there was formula and I wrote 1 over Z, and the trace is just the sum over N, N, R, N, and to the minus beta. No, trace doesn't really make sense. This would be the sum of it. Okay, it's very easy because now we can move this cat down, and what will happen, okay, it's the eigenstate, so it will just make me energy, right? And I'm just moving it, so if I'm going, then I can write it into 1 over EH, beta function, 1 over Z, sum over N. And I'm moving these over there, and I'm getting this is N to the minus beta N, right? Good. So what remains here is that I have this state N, and then I have these two operators, R, Heisenberg, and then E, this operator O, which is in the perturbation, minus O, operator R, and oh, no, okay. Okay, I wrote it like that. Good. Okay. Or maybe it would be better, let me do it better. Sorry, okay. same. So there will be the minus. I'm copying the minus. And let me call this summation index as an m. And then I will add the minus beta m. And I will call it as an m. Oh. What I did? I just this trace, I just made this one minus that one. I just write it separately. Okay? And here I am using the summation index n, and here I am using the summation index n. But the result of the sum does not depend on the name of the summation index. So remember that. Like the sign of, like the result of the integral does not depend on how it's called the integral. Okay. But you see, there is not matching. Do you see that not matching here? From here to here. Fine? Can I go on? Perfect. Now what we do, we put here the resolution of the identity. We write the identity operator in terms as a sum over all quantum numbers, m. Going like this. And I do the same thing here, that I put here identity, but written as the sum over n. And going like this. Okay? I'm using the resolution of the identity. So if I'm doing the resolution of the identity and I'm plugging it there, I can continue here. So I'm continuing, so I'm getting that it is 1 over EH. There is the theta function E divided by the partition function. And now I'm having sum over n and sum over m. And then I'm add to the minus beta energy n in the first term. And what I'm getting here is the matrix element of the operator A, Heisenberg, SIT, m, and m O n, right? From the first term. And from the second term, I'm getting this minus and the minus beta m, right? And then I'm having it the whatever this is the m O n and Heisenberg SIT n. This is some guys are saying yes. Johnny, if you put the fingers up, I like it. Like don't know, okay, clear? Perfect. Now what we can do is that we know how this guy is behaving, right? So we know that this guy is his Heisenberg picture, and this is the Schrödinger operator, and then we need to sandwich it with minus E divided by E bar H0 times E, and there is a plus E over H bar H0 times. Put it back there. But this is the good, because this is the eigenstate, so it can jump here and it can jump here, right? So the eigenstate, if I put in here n, and if I put in here n, I can put the closer here, and they will produce me the exponential factors, right? Do you see? So then I'm doing it here, and I'm doing it here. Okay? So let's do it. So we continue here. And this is 1 over EH, theta function divided by z, and again, summation over m. Great. So what I'm getting here, and let me write it already together. This would be f to the picture n minus to the minus beta n. Okay. And you see, here I have the same thing, and here I have the same thing. Okay, so I took it out, and I put those two exponentials together. Okay. So then now I'm using the following thing, the trick which I was describing you. So what I'm getting here is add to that, and now I'm getting that it is add to the minus E H bar, and this state M is meeting Hamiltonian, so it gives me E, and then will be energy M. this guy is meeting an N, but it's in the cat, so it should be like that. So it is alright. Great. And now M and N came to the Schrödinger operator. So I can just write it like that. It is the N Schrödinger. I'm not writing it M. And it is M O Schrödinger, which I'm not writing. Okay? So if I would know eigenenergy and the matrix element of this operator, so this is this Schrödinger operator. Now I can write the really Schrödinger operator. I will just need to know the matrix elements between the energy bases. So this is the called energy basis, that I'm able to find the Hamiltonian in the energy basis. I would be able to compute this following thing. And you basically see, okay, something, summation C. And then I was telling you that, of course, we wanted to have in the game also some terms to don't have the singularity, so we are putting this convergence factor to the delta. This guarantees us that if t is going to infinity, minus infinity, this thing is going to 0. We don't have the response to this thing, right? Fantastic. We are super good. What I'm doing some issues. I did something wrong. Yeah. Okay. Okay. This should be mine. I think this should be mine. Here should be minus. Because the reason for the minus once more because I was too fast. We move the perturbation to the perturbation H. We modify the perturbation H. Then we add it here delta T. So in the response function we should add minus delta T. Okay? So there is a minus. Okay. And it's fine. And it's fine. Because it's fine. It's fine because now by sign it because there is this theta function which is added there. So if theta is negative, this is a 0 already automatically. So only when theta is going to infinity, we cover it such that it's now not divergent or something like that. So if E is going now to infinity, this time is guaranteed that singularity. But the main point is like that I change the perturbation before like that, so I need to change the susceptibility like that. Such that they are canceling. Okay? Good. So this formula is called lemma for spectral representation of the susceptibility. Because we are using the spectral data, which means eigenfunctions and eigenenergies to express it like that. Okay? So if I know the matrix element in the energy basis, I will be able to compute it. Perfect. Is this clear? Can I go on? Perfect. So now we will use this spectral representation and we can make the Fourier transform. Because we are having explicitly R dependence is hidden here. This is depending on the R0, this is depending on the R. Just to save the space and don't write everything, I didn't put explicitly this thing. But all the time dependence here is explicit. Time is here, time is here, time is here. Okay? So now we can make the Fourier transformation this time. So what we are going to do, we will make the Fourier transform of it. So what we will write is the Fourier transformation. Now we wish that this expression which is there. So, okay, this is the Fourier transformation. Now I need to write this function t as a function of time. Okay. So basically you see that the all time dependence is just in here and here. So if I'm doing this Fourier transformation, then what I'm getting is that this is the sum over n. Then 1 over e bar, 1 over z. So I will make the summation. And then I have the minus beta n. Then I have this matrix element and m, n, n. Great. And now comes the integral, and the integral is the integral which you need to evaluate. I will just write it here. And the integral, and this is the integral from minus infinity to infinity, the t, and then we are having the theta function t, right? And what we get was a to the minus e bar e, and then I am having here n, where was n, minus delta. And since I'm doing the Fourier transform, omega t. By the way, this minus, I can compensate. I don't need to write minus here if I can. So we get the following integral. And now you see why we are putting here this convergence factor. Because this integral, because of the theta function, is just changing to the integral of the form minus. It's just basically integral from 0 to infinity, right? Because of the theta function. Okay? This is the integral of the following form. That this is a to the e alpha t. Okay, I put everything, all these things in the imaginary I here, plus or minus delta t. So I can integrate this integral, and this integral is a to the e alpha t minus delta t divided by e alpha minus delta. Then I need to evaluate it at point infinity and point 0. Right? But at infinity, this convergence factor kills it. Because delta is positive, delta is small positive number, so delta times infinity with the minus is minus infinity, so at infinity I'm getting 0, and then I'm getting a minus, and now I'm putting the value at 0, so it is 1 over e alpha minus delta. So now you see why this convergence factor was included, because we had I would not have it, then I would have suddenly something in infinity which is not logical. Alright? So that was the trick which we introduced to prevent such situations to happen. Okay? Quite very fine? How fine you are like on the scale between 1 and 3? Fine? Can I go on? So I will just write the result. So if I'm now making this integral, we just describe you how to do it. So final result of this thing, if I'm just doing this integration, and I think this would be everything for today, is that we are having, after this integration, which I told you, after this integration, we are getting the result, which is 1 over dh. Then we are having 1 over z, sum over m. And then what we are getting here is n to the minus beta n minus n to the minus beta m. Okay? And in the denominator, I'm getting these things. All those things actually I'm getting there in the denominator is already written. And I can also put this EH into the denominator. So at the end, my denominator will be like that. That is h power omega plus n minus n root e delta. And then I would have this 1 delta NR. But since delta is just the convergence factor, it's something we introduce artificially and we assume it's some small infinitesimal number. So h times delta is also small infinitesimal, but not now number because it has a dimension of delta was 1 over time. So delta was not a number, it has a unit because I introduced the exponent n to the minus delta t. T has a unit of time, so delta is 1 over the time, so it's a frequency. So now I can put it as a delta, but now keep the delta as a dimension of the energy. Okay, so delta should have a dimension. Everything is and has a dimension of energy. Alright? But it's a something small, it's a something of which we are at the end can ignore. But only at the end of the calculation. You still need to keep it to calculate all the observables with that, and only in the final result you are making the limit of delta going to 0, not now. Okay? This is the formula which we derived for the Fourier transform of the successibility. So we perfectly integrated out of the time dependence. And you see the life starts to look much nicer. We just really need to know the energies and the expectation values in the energy basis, and then somehow to know how to make such summation. But we will learn how to do it. Okay? That's the main thing. So we will learn how to do it, and then we will learn how to do it even for the interacting systems. Okay? So we will do it for the non-interacting systems, but also for the system, and there will be the, let's say, Hubbard interaction or the Coulomb interaction. And we will come out of that, we will discover some screening effects and things like that. Okay, so we will still continue with this formula, because this formula is basically the clue for everything that we will do, for mostly everything that we will do. So that's why I spent time to explain it. I still had prepare much more for today, but then I will continue next week about this. And also I will put to the Moodle what I need to learn how to do it, the lecture notes. I am following the lecture notes on the internet still, which I send you, and I will also make a copy and put it to the Moodle so that you can use it. And I also prepared some homework problems, but I think we can still solve the homework problems too. And so, that's all for today, I will say. So last time, Nickhouse tutored me because I was still in Slovakia, but I don't know if you have feeling that we can substitute this lecture and find a common Okay, that's everything for today. Next week we will continue with this formula and we will try to compute some response function for non-interrelated Gaussian graph. And we will compute the response of the density to density distribution. And this will be really important for the screening, for the Fermi-Thomas screening, for the random phase distribution, for the quantum, it's very important. One calculation to do, to the related groups. Also, I will include next time the concept of the second calculation. If you have any questions, feel free. If not, have a nice weekend.